So I was like, okay.
Okay. All right, it is 5 o'clock on the dot, so I think we can get started. Hi, guys. My name is Michelle. I'm a Calc 1 recitation leader, and I'll be doing the review today with lovely Angela, who's also a Calc 1 recitation leader. So this is just to kind of go over problem types and concepts that you'll be expected to know on CBE 1, which is pretty much limits, all you need to know. Ooh. Now we get into the fun game of, okay, all right. So the CBE 1 covers lessons 1 through 3, which is pretty much a basic introduction to limits and how they work. The mathematical concepts behind the limit theorems, and then what defines a function as continuous or not continuous. So this first part will be your introduction to limits. So a limit pretty much is, as x approaches a value, it is asking the question, what is the function value approaching? So as x approaches, gets infinitely close to a certain number, what is the output of that function infinitely close to that point? The key part about limits is there may be a point there that exists, but oftentimes there is not. So we're going to find the closest approximation, I guess, to the point that should exist there. We say a limit does not exist if there is no value the function approaches, and there will be multiple situations that we will cover here in a second. So directional limits approach our little x value from a specific direction. Left-handed limits are notated by this little guy here, by minus, refers to x value slightly smaller than the given value, and then right-handed limits, so this guy, refer to x values that are like infinitesimally bigger than the given value. So they're often given in the form of the limit as x approaches some number from the left, from the right, or the limit as x approaches some number from the left. In order for a directional limit to exist, coming from both sides, the number must be the same coming from both sides. But if you're only asking for the limit coming from the left, you don't think about the limit coming from the right. So with this first problem, it's asking what the limit is as x approaches 5 from the left for this piecewise function here. What do we think the left-handed side of this limit is going to include? The top function or the bottom function? The top one. Why?
It's negative. It looks like less than 5.
Yeah, so in order to solve this problem, we want to look at this. We say, hey, it's coming from the left, so we want to find values that are less than 5. So in order to solve this limit, we will just plug x in. So hang on. Let me do this. So we're going to say, hey, it's the limit as x approaches 5 from the left of 2x plus 8. So we plug in our 5, so 2 times 5 plus 8, which equals 18. And that is our solution. Does that make sense so far? Beautiful. Do you want to take over?
Sure,
Yeah.
Okay,
Nope.
Sorry.
No, you're good.
So just like she said, for the last one, in this case, we're going to be looking at x as it approaches 2 from the right. So with this equation, we can just plug in our 2 and see if it works. So I'm just going to draw an arrow down here. So we're going to plug in 3 times our 2 plus 7 on the top. And then we're going to take this and we're going to do 2 squared plus 2 times our 2 minus 8 on the bottom. So in this case, 2 times 3 is equal to 6, plus 7 is going to equal 13. And then we're going to have 2 squared is 4, plus 2 times 2 is also 4. So you have 4 plus 4 is equal to 8. 8 minus 8 is equal to 0. Do you guys remember what happens when you have a 0 on the bottom.
Undefined.
It's undefined, but in this case, as it approaches from the right and it gets super, super close to 2, it's never going to quite equal 0. So what we can do is we can just plug in something infinitesimally close to 2. So we can say from the right, we can say this is 2.1 plus 7. And we'll get something very close to 13. It'll be like 13 point something. We can say it's 13.1. And then here we have a 2.1 squared plus 2 times 2.1 minus our 8. And so we're going to get a super, 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 super small number. And it's going to be like, I don't know. Let's see, 2.1 squared, like 4.2-ish. Plus another 4.2. So we're going to get a positive number that's going to be 0.02, 0.04-ish. So if you have something really big on the top divided by something really small on the bottom, what are we going to get as it gets super, super close to 2 from the right? Close. It's not negative infinity because there's no negatives here. We have a plus on top and we have a plus on bottom, but you're correct with the thinking that it's going to equal something like that. What do you guys think? If it's a plus on top and a plus on bottom,
It's just infinity.
it's just infinity. Good. And we can see that here. Okay, any questions on this so far? Okay. I'm seeing some head shakes, some head nods. What questions do you guys have? Yeah.
So I guess maybe just to like summarize the way that you would go about evaluating this limit. But a good strategy is to first try out what X is trying to get to. And then if it is undefined in the bottom, because we're approaching from the right, just try something slightly bigger than 2. And then we determined that we're getting closer to positive infinity. Like, where was the logic for that for the denominator?
So for the denominator, if we made this even smaller, so we could say that this was like 2.000001.
Right.
That's still greater than 2. If we plug that in, we get something similar to like 13. And we would get something super, super close to 0. We would never quite get to 0 as it approaches from the right. And so if you're dividing by something super, super small by a pretty big number on top, you're going to get something really close to infinity. It's going to
Gotcha.
shoot up.
That
Yeah.
makes sense.
So you can plug in something a little bit bigger. You can plug in something super, super close to 2. What you're looking for is just how much of a difference it's going to make to the top and to the bottom. And so in this case, it's not going to make a ton of difference on the top, but on the bottom, it's going to get really, really close to 0. And so if we're dividing by a very small number, we're going to get really close to something that shoots up to infinity.
Did you have a question over there?
Yeah,
Yeah.
so if it's divided by 0, are we just able to assume that it's gonna either equal infinity or positive infinity?
Not necessarily.
Yeah, not necessarily. That's why we want to kind of check with these extra numbers here.
And another
Yeah.
thing we can do is, how many of you took 1050 here? Okay, do you remember how to find an asymptote of a function?
Take the power test, right?
Yeah, we can.
Exactly.
My first step is we factor. So if we factor the bottom, we get something like x plus 4 times x minus 2 in the bottom, I think. Yeah, that seems right. And if you notice, if we plug into here, we don't have any 2 we can cancel up top. So we know that this is going to be some sort of asymptote. So the function itself, it's going to have some sort of asymptote here. And if I remember correctly, it looks something like this. And then we have something else over here. But yeah, that's another way you can think of it, because if we're approaching infinity, we're approaching some sort of asymptote.
Yeah.
I don't know if that helped make any more sense, but if you took college algebra.
That is another, yeah, that's a really good way to think of it. Any other questions though?
It's kind of goofy to wrap your head around. You guys are doing great.
Okay, we'll move on to the next one, but if you guys have any questions, just shout them out as we go. Okay. Maybe. All right, so like was said before, if we want a limit to exist from both sides, if we want this one right here to exist as x approaches a, it needs to exist both from the left and from the right, and they also need to equal each other. And so we can kind of see that in an example that we'll go over. So in this case, we have a piecewise function. So as it approaches 5 from the left, which equation are we going to use?
Bottom one.
Bottom one or
From the left.
from the, sorry, from the left. So
Yeah.
as the limit,
direction.
Yeah.
oh my goodness, my handwriting is terrible. So as it approaches from the left, it will be the top function, because this right here, it shows the x is less than 5. So it will be something on the other side of the function before it reaches 5. So it'll be getting close to 5, but not quite 5 at this point. Okay, so if we plug this in, we can say that 2 times our 5 plus 8, we found that before, that's equal to 18. And then if we're wanting to see if x approaches 5 from the right, which one are we going to use?
The bottom one, or bottom one,
The bottom one, why?
because it's on the right side.
It's on the right side and it also is equal to 5. So, okay, awesome. So we're gonna plug this in. So we'll have 5 squared equals 25. Okay, do 18 and 25 equal each other? They don't. So in this case, the limit as x goes to 5 of this function will not actually exist at 5. It'll be something like this. You'll have like a graph and you'll have a line, and then you'll have like another line that looks like this. But at this point right here, where it's actually equal to 5, I mean, this isn't 5 over here, it's over here somewhere. Whee! But this is going to be probably a point like right there or something. So it's going to be like a jump, so it's not going to actually equal each other. Any questions on this one? Okay. So in this case, it doesn't exist. We can just say D and E.
All right, so in this one, we're asked to evaluate the limit as x approaches 16. And if we see this square root in the denominator, our first instinct is generally to panic, but we don't want to do that. If you guys remember conjugate multiplication, what we can do is we can multiply the top and the bottom by a fancy way to say 1. So what we're going to do is we're going to have the limit as x approaches 16, x minus 16 over square root of x minus 4. Oh yeah, this limit does not work, because if you watch, if we put 16 in it, we have 16 minus 16 up top, and then square root of 16 minus 4 up bottom. So we have 0 up top, and then square root of 16 is 4, minus 4 is also 0. So we need to do some fancy math here. But in order to get rid of the square root in the bottom, we're going to multiply by square root of x plus 4 over square root of x plus 4, which is a fancy way of saying 1. And when we do that multiplication, we just FOIL it out. We get the limit as x approaches 16 of, I'll just do this, x minus 16 times square root of x plus 4 over square root of x times square root of x is x. Square root of x times positive 4 is positive 4 square root of x. Negative 4 times square root of x is negative 4 square root of x. And then negative 4 times positive 4 is 16. So these terms go away right here. And we are left with the limit as x approaches 16 of x minus 16 square root of x plus 4 over x minus 16. I see two terms that can cancel here, and right here. So I'm just gonna scoot it over here. We get the limit as x approaches 16 of square root of x plus 4. Now we can plug it in. So if we plug 16 in, we get square root of 16 plus 4, which is equal to 8. And our answer says it's 8. Does that make sense so far? Perfect. Yeah. All right, so now we want to evaluate this limit here. Our first order of operation is to plug it in to see if it exists, but I'll tell you right off the bat, it's not going to, because if we just plug it into the denominator, we get 11 squared minus 121 over something. 11 squared is 121, so 121 minus 121 is 0 in the bottom. So we're gonna have something up here. I don't know if it exists or not. Moral of the story though, we need to do a little more work. So what I'm gonna do here is I'm going to factor the top and factor the bottom. The bottom is pretty simple to factor. This is a difference of two squares because we have a square term right here and a square term right here. So we're gonna have an x plus 11 times x minus 11 in the bottom. And then up top, I'm gonna factor out a 3, just so I can see the base polynomial a little bit better. Now that you can see what I'm writing, can you see this? No. Okay, good. We'll just ignore that. So we get 3 pulled out of 39 is, well, negative 39 is negative 13x. 66 divided by 3 is positive 22. And this is actually a lot easier to factor. So what we're gonna have, the limit as x approaches 11 of 3 times, so we need something that when multiplied together equals 22 and when added together equals negative 13. And fortunately we have x minus 11 and x minus 2 that will fulfill those requirements. Because if we multiply negative 11 and negative 2, we get positive 22. If we add negative 11 and negative 2, we get negative 13. Perfect. And then x plus 11 times x minus 11. I see something that can cancel. Zoop, zoop. So we're left with the limit as x approaches 11 of 3 times x minus 2 over x plus 11. And this is something we can solve. So we have 11 plus 11 in the denominator, which is 22. And then 3 times 11 minus 2 up top. 11 minus 2 is 9, times 3 is 27. So our limit is 27 over 22. And that is our solution. Does that make sense? It's kind of gross factoring, and it makes you remember all the factoring things you learned back in college algebra or 995, but it's good information. Yeah.
Alrighty. So when looking at graphs, kind of like what we discussed before with the limit has to approach the same number. Here it's a little bit more visual, which is really nice. And so when we're looking at this graph, we're seeing from the left, what does this go to? So if we're looking at x approaches 4 from the left, what do we see on this graph?
The numbers are a little hard to see, so
It's
sorry.
going to approach. I wonder if I can zoom.
You
Oh,
can.
wow, look at that. Okay, what is this approaching right here? So as we plug in 4 for our x, what are we getting close to on the left? I'm seeing 2 on some people's fingers. Yep, 2. Okay, as we're approaching it from the right, what are we seeing it approach? 2 as well. Good. So right here, the limit is equal to the same number. So we can say that this is equal to 2, which is what we get. Any questions on this one? Okay. All right. So in this case, again, we have to check to see if as it approaches pi halves from the left and as it approaches pi halves from the right, since we don't have a visual, we'll have to do it mathematically, but we want them to be the same value. So as it approaches it from the left, which one are we going to use? The top one, exactly. So I'm just gonna use this up here. So we're gonna have the limit as x approaches pi halves from the left, we're gonna use this top one. So we're gonna plug this in. We're gonna say 2 sine of pi halves. And do you guys remember what sine of pi halves is? I'm getting 1. If you don't remember, that's okay. I always have to draw this out. So this is 0, this is pi halves. And so I just plug this in and this is 1, 0. Wait.
Yes. Well, 0,
0, 1. Thank you. Hold please. I can totally remember how to do this. Okay, this is pi halves and this is 0, 1. There we go. That looks a little bit better. Okay, awesome. This right here is 1, 0. All right, so we're looking at the sign, so we're looking at this value right here. So whoever said it in the back was correct, it's 1. So this is going to be 2 times our 1 is going to equal 2. Okay, as the limit as it approaches pi halves from the right, which one of these are we going to use? The bottom one, correct. Why?
Because it's coming from the right.
Correct. As it's coming from the right, it's gonna get really close to that pi halves. Good. Okay, so we can go ahead and plug this in. So we're gonna plug in cosine of pi halves plus 2. So we're looking now at cosine of pi halves, which is this x value. That's gonna be our 0. So we're gonna plug in 0 plus 2, which equals 2. Does 2 equal 2? Sounds like a weird question, but we have to check. I'm seeing some head nods. 2 equals 2. So therefore, the limit of this is equal to 2. Okay, any questions on this? Alrighty. Okay, infinite limits. This is when we plug in positive or negative infinity. We're going to see if it gets close to a number or not. So would you like to
Sure.
take one of these
Yes.
ones?
Oh, this was a fun one.
Oh yeah.
All right. So this one's a little weird, but it's nothing we can't deal with. So the basic shape of a sine graph, so it looks something like this. So as we go off into infinity, sine is going to be permanently stuck between some number, +1 or -1 down here. So we're going to have the limit as x approaches infinity up top is going to be a constant, either something between -1 or 1. The limit as x approaches infinity on the bottom, 3 times infinity is just some flavor of infinity. So we're going to have infinity in the bottom. So we're going to have a constant up, some pretty constant number up top, and then something approaching infinity on the bottom. A number over some infinitely large number, that's just approaching 0, right? Seeing some confusion.
Do you want to give them an example of like a super, super big number?
Yeah, so I guess what we could do is say we have at some point 300, we have some value, sine of some number equals -1 up top. And then at that point, we're gonna have 900 in the bottom. Is -1/900 pretty darn close to 0? Yeah. So the solution is 0 because we're gonna have some pretty stable constant up top and then some wacky large number in the bottom. All right, so this one, evaluate the following limit as it approaches infinity. My trick with these ones in particular is, okay, so it's approaching infinity. And if you look at this term here and this term here, they have the same degree. So I'm just gonna ignore all of these other terms over here because once you approach infinity, 7 really isn't gonna do much for you. And once you approach infinity squared, some other infinity over here and a -1 are also not gonna do much for you. So the terms we wanna worry about are 4x squared over x squared. And if you notice, this term cancels with that term, that cancels with that term. So the limit as x approaches infinity of this should be 4. It's kind of throwback to college algebra as well. Does that make sense?
Pretty simple.
Yeah, this only works for limits that approach infinity. This little trick. If it's approaching some definitive number, you're gonna have to simplify somehow.
So it
But
was x over like x cubed. What would you guys do for that one?
Did you factor it?
You could factor it, yeah, but if you have like a 4x over an x cubed on the bottom as it
So-
approaches infinity,
we have a number up here and then we have x squared down here.
Isn't
What?
it also 0?
Yeah, that is 0. Yeah.
if it was a 4x over x squared, what would you guys have?
Be 0.
Yeah.
Still be 0. So yeah, looking at the amount of things being squared or cubed or whatever you have, you're gonna look at how big it is compared to the other ones that you have.
The leading terms
Yes.
usually the highest. You worry about the highest power with these polynomials. Yay, limit theorems. You wanna do this part?
Oh, sure. Okay,
So there's a whole bunch of rules that basically what it's saying is if you're looking at a limit from one thing, you can add it to a limit of another thing once you find the limit of one thing or another thing. So in this case, if we had a limit as it approaches a function of x, and you're wanting to know what it is from f of x and from g of x, you can kind of just split it apart and be like, okay, well, I'm just going to check this first one out. I'm just gonna see what it is in f of x. And I'm also just gonna check it out from g of x. And from there, I can add them together. Same with multiplication. If I'm looking at what I'm wanting from both f and g, you can split them up and you can say, I wanna find f of x first, and then I'm going to multiply whatever I get from f of x by whatever I get from g of x. And we'll kind of go along with some of those. But basically what they're saying here is anything that you have as far as addition, subtraction, multiplication, division, or you're multiplying by a constant, you can kind of just move the limit over and you can kind of separate the different things that you guys are wanting to add, subtract, multiply, or divide. So we'll go over an example of that. So on this one, we're gonna start with this guy up here. So we're wanting to find the limit of f of x plus g of x. So in this case, we can separate them and we can say, well, first we're going to find the limit as x approaches -4 of f of x. We're not even gonna touch g of x right now. We're just wanting to see what it approaches for f of x. So for f of x, this guy right here, we're going to have it approach -4. As it approaches -4 from the left, what are we going to get? I can zoom in here. This is 1. So as it approaches it from the left, we're gonna get 1. Good. Okay, as it approaches it from the right, what are we gonna get? Also 1. Good. So this limit exists. We can actually find this limit. So right here, for f of x, this is 1. Awesome. Okay. So we know what it is for f of x. Now we're going to look at g of x. Woo, it actually stays put. Okay, this is 3. I'm just gonna draw that. Okay, as this approaches 3 from the left, as this function approaches,
Should be 4.
is it 3? Oh, it's 4. If it approaches 4, sorry, this number right down here is 4. I'm looking at -3, 1. But as it approaches 4, what are we going to get for both the left and the right?
3.
Good, 3. Okay, so basically what those functions were saying before is you can take this one right here for f of x. We're just gonna plug in a 1 for this. And then right down here where we found our 3, we're just gonna plug that in to this. So we found the limit of -4 of f of x, and we separated it, and we found the limit of g of x as it approaches -4. So the limit of all of them together as x approaches -4 is going to be 1 plus 3, which is 4. Okay, any questions so far? Okay, awesome. We're gonna move to the second one. So now we have f of x times g of x. We already know what each of them equals because we found the limit as x goes to -4 of f of x, that's equal to our 1. So we're gonna have 1 here. And then we're going to have the limit of x goes to -4 of g of x, which we have found was our 3. So now we're just going to multiply these together. So the limit as x goes to -4 is 1 times 3, which is just equal to 3. Okay, any questions about any of these?
So it says on the bottom that there's solutions 4 and 3.
Yes. So
Um,
right here, this was the first one. So this one was equal to 4.
Oh, okay, I see now.
Yeah, you're
Or
good.
you
No,
do 2 separate
we're just doing 2 separate
Yeah,
problems
that's-
into one.
okay,
Yeah.
that's-
So then this one was 3.
Yeah.
Yeah.
Conserving space.
Exactly. So if I was to ask you guys this, if I wanted to find the limit as x approaches -4 of f of x
That's the next slide.
over g of x, oh, just kidding.
I think it's different functions.
Thanks. Okay, well, we're gonna go over some more. Here we go. Okay, just kidding. But we're gonna do something very similar.
I can
Do you wanna
this part if
do
you
this
want.
one? Yeah.
Yeah, so pretty much, let's see, we're gonna have it approach 1 from the -1 from the left this time. And we're gonna divide the limit for g of x by the limit for f of x. So if we approach -1 going from the left, that is, -1 is right here. So we're gonna approach it coming from the left, approaches -1, and if you look right here, we have a -3 right there. So we're gonna have a -3 for g of x. So limit as x approaches -1 from the left of g of x is -3. And same idea over here. So we're gonna approach -1 from the left. Oh no, here's -1 right here. We're going off into infinity, aren't we? So we have some number up top, a constant, and then we have an infinity in the bottom. What is that approaching? Yeah, it's approaching 0. Because we're dividing 3 by an infinitely larger number. All right, same idea for f of x and g of x. So we found our limit for f of x, which is infinity, positive infinity. And then we have -3 for g of x. What is infinity divided by -3? Yeah. That should be our answers, yes. Does that make sense? Cool. All right, so that is all for this review. We have more videos and resources on the Aggie Math Learning Center webpage. It should have a link to our YouTube and our tutoring hours. We have tutoring from 10 to 2 tomorrow in here, in next door if you want to swing by. Otherwise, thanks for coming. Have a good night.